Mm, So even though my title was Evolutionary Games in Finite Populations, I decided to modify it a little bit because my first lecture, which is today's lecture, will not be talking about game theory much because I have to set the framework for eventually start talking about evolutionary games in finite populations by first talking about evolution in finite populations. So, so this is outline of the 4 lectures that I'll be giving. So in today's talk, I'll be focusing on just evolution in finite populations, and I'll explain how it's different from evolution when games are taken into account. And in this, there are 3 different categories that one can talk about with increasing levels of complexity. We can first talk about evolution with mutation but without selection, then evolution with selection but no mutation, and this is the part that we will focus on extensively during the subsequent lectures. And finally, the most general case where you have evolution with both mutation and selection. Okay. And in tomorrow's talk, I'll be talking about evolutionary games in finite but well-mixed populations where there is no underlying structure to the population. And finally, in the last 2 lectures, I'll focus on games in structured populations. Okay, so I think you have heard a lot about dynamics and games and networks already, but not much has been said about evolution as such. So this is just a slide to highlight what I mean by evolution when I talk about evolution of populations, and I'm talking about evolution in a Darwinian sense. So you can think of a population of individuals with different types. The types can be different genomes, they can be different species, and so on. You can keep it as general as possible, and they can undergo mutation during the process of reproduction, which leads to new variants, and mutations cause variation in the population, and selection acts on the variants and tends to select those which have higher fitness with respect to the environment in which the population is evolving. The key point here is that evolution is a stochastic process. So even though common sense notions of evolution that you may have heard of tends to portray the idea that evolution means survival of the fittest, that's not always the case. Higher fitness individuals are not guaranteed to take over the population, but are more likely to do so than is expected by chance. And I'll quantify what I mean by these statements in this talk. Okay, so you may have come across the replicator equation. So I'll start off this slide by generalizing the replicator equation a little bit by taking into account mutations as well, which leads to an equation called the quasi-species equation, which was developed by these 2 gentlemen, Eigen and Schuster. Eigen won the Nobel Prize in chemistry for his work on chemical kinetics. But they developed the quasi-species equation mainly to understand evolution in a very primordial context before life had emerged. There were just sequences of different types, say RNA sequences mostly, and they were evolving as a result of mutation and selection. So you couldn't think of them as distinct species, these different types of RNA sequences, but some sort of quasi-species which could transform from one to the other, and so on. And this led to the evolution of a population of such sequences with quite interesting consequences. So the replicator equation, which you have probably come across by now, is just a limiting case of this quasi-species equation, where where this mutation matrix here, which is represented by Qji, is a diagonal matrix with all the diagonal terms being identity elements. And so, in the limit where there is no mutation, where Qji can be replaced by Kronecker delta Ji, then you get back what is called the replicator equation. And the point that I would like to emphasize is, as far as taking into account evolution by this equation, this quantity is a fitness. So, this is an equation which describes n different types of quasi-species that can mutate from one to the other during the course of evolution. Each of the types have a fitness ascribed to them, which is constant, and they have a frequency associated with them, which is given by xj. So, xi's are the frequencies of the different types of quasi-species that are present in the population, and this is a dynamical equation which shows how the frequencies evolve with time. The key point here is that the fitness is constant. So, this is an approximation that I am going to relax in tomorrow's lecture, where I am going to talk about situations where the fitness is frequency dependent, which is going to bring game theory into the picture. So, for constant fitness, if you look at the case of selection without mutation, the Qji is a Kronecker delta, so which drops out of the picture, and this equation reduces to this one, where phi is the average fitness of the population. Now, if you have just two different types in the population, the equations becomes uncoupled, and because x1 plus x2 or xa plus xb must add up to 1. These are the two frequencies of the two types, and so this is how the uncoupled equation for xa, which is a frequency of type A, looks like. So, what does this tell you? It tells you that there are equilibrium states possible, and there are only two possible equilibrium states for which xa, which correspond to xa equal to 0 or xa equal to 1. So, as a result of evolution due to competition between two different species with two different fitnesses Fa and Fb, only one of them is going to survive at the end, and which one survives depends on which has the larger fitness. So, if Fa is larger than Fb, dxa dt increases with time, and eventually xa hits 1. If Fa is smaller than Fb, then it decreases with time, and eventually xa hits 0. So, B takes over the population. So, this is a situation where as a result of competition without mutation, only one of the two competing types survive in the population, and the type which survives depends on which has the greater fitness among the two types. Okay. Now, this is an intuition that is based on a deterministic system described by a replicator equation, but this equation has to be revised when we go to finite populations. So, I am going to go back and forth between deterministic dynamics given by the replicator equation or this kind of equation without selection, and the stochastic dynamics where you have evolution in finite populations, to highlight the differences between the two. So, first let us look at a case where there is mutation without selection. And suppose I again take two types of species, assuming that one can mutate to the other, and suppose x1 and x2 are the two types. So, I can write down equations for x1 and x2, which are the frequencies of the two types, as minus u1 into x1 plus u2 into x2. How do I get this equation? So, this tells me that x1 can be type 1 can mutate to type 2 with rate u1, and so as time passes, the amount by which the type 1 changes will depend on how many of them mutate to type 2. But then back mutations are possible. Type 2 can mutate back to type 1. And so these two counterbalance each other, so at equilibrium. And so at equilibrium, we have x1 dot equal to 0. And I can write x2 as 1 minus x1. So at equilibrium, the frequencies are given by u2 by u1 plus u2. And similarly for okay. So if you track the population, and I'll talk about agent-based simulations that one can do by starting off, say, at x1 equal to 0.5. So how is the population going to evolve? It is eventually going to reach these steady states determined by these values of the frequencies, where u1 and u2 are the mutation rates from one to the other. But suppose we start with a population where the two frequencies are the same, and again, depending on the values, so one will keep fluctuating like this and eventually stabilize. So another might decrease a little bit, but there will be fluctuations. Okay. So what has this got to do with finite population dynamics? How is the dynamics going to change in finite populations? So this is something that you will observe when, say, the population size is of the order of 50 or so, right? So the smaller the population size, the larger will be the fluctuations in the frequencies. And the reason is that when the population size is smaller, the changes in number from one time step to the other can be quite significant compared to the size of the population. Okay? And that leads to these large fluctuations that you observe for small population sizes. But if you look at, say, n equal to 1000, the curves that you observe will be a lot smoother, and there'll be tiny fluctuations, but mostly it'll be like a straight line. So in fact, if you look at if you plot the fluctuation, say at any point of time after the curves have equilibrated, you calculate the frequencies and do it repeatedly for a large number of trials and calculate the variance, which is so this is going to go as 1 by n. So as the population size becomes larger and larger, the fluctuations will become smaller and smaller, and you will get and you will approach the infinite population limit, where the curves become absolutely smooth. Okay. So how do we carry out these simulations? Since you are doing projects and you maybe some of you know a bit of programming as well, so you can try out these simulations, which is pretty simple actually. So you need to start with two types, and initially you can have 50% of each type in the population, and so you go through the population, you sweep through the population every member at one member at a time, and you check whether this is going to mutate or not. So you generate a random number, check if the random number is smaller than the mutation probability for this type, and if it is, then you mutate, otherwise you don't. And then you move to the next one and keep repeating it until you have covered the whole population. And at every time you calculate the frequency of each type in the population, and you will and if you plot the frequency with time, you will get a curve like this. Okay. So yeah. So u1 is the probability with which type A changes to type B, and U2 is the probability with which type B changes to type A, right? Okay, so this is one difference that you come across when you go over from a deterministic infinite population dynamics to a finite population stochastic dynamics. You see, at least as far as evolution with mutation but without selection is concerned, the frequencies would keep fluctuating a lot more for small population sizes, but would smoothen out as you go to larger and larger populations. Okay, so this is just the algorithm for doing that. In case any of you would like to try it out, I'll put up the slides later on and you can try it out. Okay, so now let's look at another situation which goes back to this. Yeah, sorry. Yeah.
So one type goes to another means a mutation.
Yes.
So like every time step A can go to B and next time step B can go to A.
Yeah. So if you look at this example here, what has happened is you have to go through the population one member at a time and check whether they mutate or not. Every single member is not going to mutate, right? So in this case, this one has mutated, and so in the next time step it has become type B, and another member has mutated, this one has mutated and it has become type B. And yeah, so this has mutated, it has become type A from type B and so on. So the net change in number occurs over time.
So again at time P plus 2, then red can become blue.
Yes. So this process can continue, but eventually it's going to equilibrate. So the frequencies of the two types will become almost constant, because and determined by these values.
So what I'm asking is consecutively mutation in a particular site.
Right.
Like how in a real life example I am trying to.
So this is a very idealistic example where I have two types and I'm just assuming that one type mutates to another. So some mutations happen inside some sort of bacteria or quasi-species, which changes over to some other quasi-species. That's it. So the real life situation is much more complicated. You just don't change from making one mutation, right? So this is just an idealistic example. Okay. Okay. So yeah.
Is not dependent on, it's not deterministic in any way, right? Like it's not dependent on its state in the past time steps.
No, U1 and U2 are just probabilities with which one type is mutating to the other.
And that doesn't change over the...
No, that doesn't change over time. Yeah, so those are fixed. Those are determined by... Okay, so now let's look at the example where there is no mutation, but there are still two types in the population, and but now there's no difference in fitness between these two types. So type A and type B has the same fitness, right? And now I want to evolve a population which consists of a certain distribution of type A and type B initially and see what I end up with. So what would you expect? Suppose there were say 50% of type A and 50% of type B in the population initially. Guess?
So a large enough population is expected to stay at the same state before the
Large enough population?
expect on average to continue staying at 50%.
Well, that never happens, right? So yes, so that's again deterministic intuition, but that's no longer true for a finite population model. Because in finite population, there are only what are called two absorbing states. And those two absorbing states correspond to one where only A types exist and another where only B types exist. So, regardless of where you start off with, you are eventually going to end up in a state where the entire population consists only of type A or of type B. Okay? And it's actually possible to calculate the probability that one of the type is going to take over the entire population starting from some given initial condition where there are certain numbers of that type in the population, and I'll do that in a moment. Okay. So, how do you do these simulations? Again, you take a population where there are two types and you pick one at random for death and one at random for reproduction. So this is a special type of evolutionary process that I am talking about, which is called the Moran process. And in the Moran process, the population can change by at most one. Why? Because suppose I pick this for death and I pick this for reproduction, then the number of type B increases by 1 and the number of type A decreases by 1. Okay. Now, I could have done the other way around, but at any point of time just one member is picked for reproduction and another member is picked for death. Right. So, the relative change from one time step to another happens in such a way that the numbers of each type does not increase by more than 1. It can stay the same when this is picked for reproduction and say this is picked for death. The same types are picked for both reproduction and death, so they are the same. So that's how the evolution proceeds. So this is a very specific type of evolutionary process. You don't have to stick to this type of process. I'll talk about another process of evolution called the Wright-Fisher process in a moment. But this is useful because it allows you to derive some analytical results. Analytical results which tell us, given our initial configuration, what is the probability that one type will take over the entire population. Okay. Okay. So let's lay the groundwork for the analytical calculation. Yeah.
How do you intuitively argue either only one of the types will get fixed because both of them have the same fitness?
Yeah. So because it's a stochastic process, right? So if you things are the numbers of each type is changing at random, right? But eventually certain one of those types will increase its number just by random fluctuation, and then when it increases its number significantly over the other type, it has a larger chance of being picked. And so that advantage builds over time, and eventually it can take over the population. So I'll maybe show you a simulation which okay, so what we want to ask is if there are two types in a population, I want to calculate what is the fixation probability of one type, say B, given the fact that there is no fitness difference between the two types, right? So how do I frame the problem? Suppose xi is the fixation probability So what do I mean by fixation probability? It is a probability with which A can take over the population starting from a state where there are I members of type A and n minus I members of type B, where the total population size is n. Okay. And so Pi I minus 1 is the transition probability So in this case, the number of A decreases by 1, and okay. So I can write down a recursive equation for xi in terms of these two quantities. So I can say that xi equal to So what does this equation mean? It means that starting from a state where there are I members of type A, I can, as a result of a Moran process, go to a state where there are I minus 1 members of state type A, and then this population can get fixed from that state, right? So this happens with probability I to I comma I minus 1. Alternatively, I can go to a state where there are I plus 1 members of type A and then get fixed from that state. And if other is nothing changes, so I stay in the state I with probability Pii, and then it gets fixed. So there are these relationships between these transition probabilities Pii I minus 1 plus Pii I plus 1. So all of them must add up to 1.
I comma I minus 1 shouldn't be I minus 1 to I, then x equal to p.
No. So I comma I minus 1 means that it goes from state I to state I minus 1.
So if you multiply that with xi minus 1, which is the
And that is the probability of fixation. So I'm asking, what is the fixation probability starting from state I? So the fixation probability can be calculated in 3 different ways. The system can stay in the state I and then get fixed. It can go to a state where there's one less of type A and then get fixed from there, or go to a state where there is one more of type A and then get fixed from there. Okay. Okay. So you can set up this equation. If you are a bit confused, please feel free to ask. But so I need to know, in order to solve these equations, I need to know these quantities, these transition probabilities, right? So for a neutral case, what is the transition probability? So what is the probability of picking an individual for reproduction and another for death? So remember that there's no fitness difference between the two. So the probability of choosing A for both reproduction and death would be proportional to the frequency of A in the population, right? So probability of picking A for reproduction would be I by n, and the probability of picking A for death would be I by n as well. So what does this lead to? This leads to no change in the net number of A's in the population. What is the probability of choosing B for both death and reproduction? The number of B's are n minus I, so the frequency is n minus I by n, so it's proportional to the equal to the square of the frequency of B's in the population. So you're picking B for death with probability n minus I by n, and B for reproduction with n minus I by n. Okay. So probability of choosing A for reproduction and B for death, A is chosen with a frequency of I by n, B is chosen for death with frequency n minus I by n, and this leads to an increase in number of A. So this gives me the transition probability that I had defined. And similarly for the case where B is chosen for reproduction and A for death, I can write down this transition probability. Now, starting from this equation, I can just do a bit of algebra, and I'm not going through that in detail here, and solve that equation for different values of I. I was the number of A's to begin with, right? So the simplest case is for I equal to 1. So then I'm asking the question, what is the probability that A will take over the entire population if I had started from an initial state where there was only one A and all the other n minus 1 members were B's? Okay. And what would you expect? This is a chance event. There's no selection between A or B. You would expect that A would be able to take over the entire population with a probability which is given by the fitness of A, by the frequency of A. And for when you start with a configuration in which there is just one A, so the fixation probability of A would be given by 1 by n. So this is the neutral evolution result, where there is no difference in fitness between A and B, and if you start with a population where there is just one A to begin with, A can take over the population with a probability given by the inverse of the population size. Now, this intuition is very different from what you would expect for the deterministic finite infinite population dynamics. Why? Because in the deterministic infinite population dynamics, if you go back and look at this equation, these two have the same fitness, right? Fa and Fb. So it tells me that any initial configuration with any frequency of A and B would be a stable state of the system. So the system would not evolve at all, right? But that's not what's happening. In a finite population, just by chance, one of the two types is taking over the population. And the probability with which one of the two types will take over the population will depend on the initial frequency of that type in the population. Okay.
Can you go back
Yeah.
to the previous slide? So here the transition probabilities are equal.
Yeah, so this is a special case. This neutral evolution is a special case where the transition probabilities are equal. So that's why this summation simplifies to just n minus 1, and that's how you get 1 by n. Okay. Now, but in deriving these results, these expressions for the fixation probability, I have not used the fact that these transition probabilities are equal. So this result is a very general result, which is valid regardless of whether you are looking at neutral evolution or evolution with differential fitness between the two. Okay. And so here's a summary of this whole evolution picture, a neutral evolution model, where initially you start with some configuration of A and B, and then just by chance A's, which are represented by these blue figures, they increase their frequency a little bit, and when they increase their frequency, the probability of selecting A for reproduction becomes larger, and that leads to further increase in frequency of A, and so on, and eventually it takes over. So the fixation probability, which is the probability with which a type will get fixed in the population and take over the entire population, depends on the initial frequency of that type in the population. Okay. Okay. So how does this change when I relax this condition that the fitnesses of the two are equal, and introduce a bit more complexity into the system by saying that the two types differ in fitness. The fitnesses are still constant. I am still working within the framework of normal evolution with constant fitness, but now the fitnesses of the two types can be different from one another. Okay, so here is an example of what happens when the fitnesses are different. So suppose type B has a fitness equal to 1. I have not written it down here, so just let me say that and R can be either greater than 1 or R can be less than 1. So A can have a selective advantage over B, or it can have a selective disadvantage over B. So in order to answer the question of what is the likelihood that type A, which has a slight selective advantage over type B, takes over the entire population, starting from an initial state where only one member of type A was present, all I need to do is to calculate these transition amplitudes and plug it back into this formula here. Okay. So how does the transition amplitude change? So here, because the fitnesses are different, I am carrying out the reproduction process with a probability proportional to fitness. The selection is no longer random. So reproduction happens with a probability proportional to fitness. The fitter individual has a greater likelihood of being chosen for reproduction and taking the place of another individual which has been chosen for death at random. So death happens at random, reproduction happens with a probability proportional to fitness. Now, what is that probability? So this is the probability, the total fitness of the I individuals which are there in the population, each of them having a fitness R, and this is the total fitness of the population, right? This is the fitness of I individuals, each with fitness R, and this is the fitness of n minus I individuals, each with fitness 1. So this is the average fitness of type A in the population, I of which are present in this time step. Okay. And this is the probability of picking B for death, which is done at random. So it just depends on the frequency of B in the population. Okay. So this is how the number of A increases by 1, leading to this transition probability. The number of A can decrease by 1 when B is picked for reproduction, and B is picked for reproduction with a probability proportional to the fitness of B, which is given by this quantity, and A is picked for death with a probability proportional to the frequency of A in the population. And when you plug in this back into the formula that we obtain, so this is something that you get. So in the case where A has a selective advantage over B, the fixation probability of A starting from a state where there was just one A to begin with is not guaranteed, right. So this is again going counter to the normal intuitions we have based on infinite population dynamics. So in infinite population you would say that of individual which has a higher fitness will take over the population, because if F A is larger than F B, the only stable equilibrium state is one with X A equal to 1. That is not guaranteed in this case. So you can see that even for a large population size, the possibility that A will take over is not 1, it is sort of modulated by this factor, right. So here is an example which hopefully will show you how the fixation probability changes as the selective advantage or disadvantage of one type changes relative to the other. So B had a fitness of 1, so the larger the value of R compared to B, the greater is the fitness advantage. R equal to 2 means that A has a advantage of 100% over B, which is unheard of in biology, right. So even with that high a fitness advantage, the probability that A can take over the entire population starting from a state with just one A out of n is just 0.5. As you decrease the fitness advantage of A relative to that of B, this is a 1% fitness advantage of A, the fixation probability of A gradually decreases. So you can do these simulations, and one thing that you should be careful about when you are doing these simulations is that your simulation should be informed by these numbers, right. So that is why analytical results are so valuable, because it helps us to benchmark our simulation results. So how do we calculate fixation probabilities? We have to run the simulation once, and at the end of the simulation only A or B will be present. That is one trial, but that can happen by chance. So you have to calculate the fixation probability by running the simulation for multiple trials, right, starting from the same initial condition. And when you run the simulation over multiple trials, suppose you run it over 100 trials, right, and so then you would expect to find that out of the 100 trials, a certain number of them A will get fixed in the population, and in the remaining B will get fixed in the population, because every trial has to end with either A taking over or B taking over, right. And so the number of trials you have to run to get a reasonable value has to be based on the fact that these numbers are quite small. So if you say for this case run a simulation for 100 trials, you will say 50 trials or 10 trials, you will not even find, it is likely that you are not going to find even one case where A gets fixed in the population. So you have to, if you run a simulation for 1,000 trials, then on an average you expect that 16 out of those 1,000 trials A will get fixed in the population and take over the population. Okay. So similarly in this case, if you run a simulation for 10 trials, it is quite possible that all 10 trials will result in A not getting fixed, right. So for a case with selective disadvantage, the results are even more striking. For a 1% selective disadvantage, the fixation probability decreases quite a lot. It's of the order of 10 to the power minus 3. So, on an average 6 out of 1,000 times A will get fixed if it has a selective disadvantage with respect to B. Okay. And but the key point is a selective disadvantage doesn't guarantee that it will never get fixed, which is what our infinite population intuition was telling us, that the fitter variant will always take over the population. Because population evolution is a stochastic process, it is possible that even lower fitness variants can take over the population. Okay, so so this is again a cartoon which shows how the population evolves. In the case where there's no mutation, there are only 3 absorbing states because there are 3 types. In one case, even if the fitness of the blue type is larger than the fitness of the others, the blue type can take over the population, but it's not guaranteed to happen all the time. Sometimes even the lower fitness variant can take over the population. Okay. This is the algorithms. Okay, so here's an I'll sort of talk a little bit about this and I think end for the time being. So here's an alternative to the Moran process update, where you instead of updating the population by at most one individual at a time, you change the entire population altogether when you are updating it. So this is a process of evolution called the Wright-Fisher process, and this is an example which shows how this is a case of evolution with 2 types, where one type has a larger fitness than the other. And so what you do is you have a population with an initial configuration like this. Suppose B is picked at random. Suppose A had already been picked, and then you pick B for reproduction with a probability proportional to the normalized fitness of B. The normalized fitness is FB by FA plus FB, and you generate a random number. If that random number happens to be less than the normalized fitness of B, then B becomes a member of the population in the next generation. And in this way, you fill up the entire population one at a time. So the entire population is getting updated at every time step. So the difference between the two is that this is a faster process, especially with a large selective difference between the 2 types. It is in principle possible for a population to go from this state to a state where only A is present or only B is present just in one go, because you are changing the entire population at one go. And but in the limit of weak selection, this mode of population updating is similar to the Moran process that I had talked about, where the population can change by at most 1. So yeah, okay, so do I have more time? 5 minutes? Okay. Any questions up to this point?
So biologically, what is the difference between these 2 settings, right?
It's just a faster.
Two different situations in nature, or
Yeah, so when you have non-overlapping generations, the Wright-Fisher process is a useful process to have, because the entire population is getting updated.
so can we think of them as generations, different like?
Yes, absolutely. Yes. So different time steps are different generations, and so the population structure changes at every generation. because the frequency of each type changes at every generation.
B becomes the second member of the outgoing population at t equals to 2.
Yeah.
So where did the first member come from?
Oh, by the same process. So I have already put in the first member. I had selected the first member, which happened to be A, and then I choose the second member. And once I have chosen the second member, I go on and choose the third member and keep doing it until the entire population is filled up.
And the probability of like choosing B or A depends on their
Relative fitness, yes. Okay. Okay, so I'll take just 5 more minutes to highlight one of the really counterintuitive features of this quasi-species equation, which includes both mutation and selection. Okay, and so we have been told for a long time, whenever the notion of Darwinian evolution came up, that the key feature of Darwinian evolution is survival of the fittest, right? So I'm going to give you an example where that is not true, and in fact the fitter variant actually drops out of the population. And so this is a paradox called the Eigen-Schuster paradox, which was first formulated by these two people when they came up with the quasi-species equation. And so here's a situation that I want to try and work out. So I have a simple model where there are two types, type 0 and type 1. Now, type 0 consists of a sequence of length L, so you can think of it as sites which are of length L, and each site can mutate, but whenever one site mutates, any site mutate in this sequence, it changes over to type 1. Okay, so this is an ideal model, but it's still a very useful model. I'm also going to assume that so any mutation at a site I'm also going to assume that the fitness of type 1 is 1, and this is so type 0 is a fitter variant compared to type 1. Okay, but the other assumption is that type 1 to type 0 is not allowed. So type 0 can mutate to type 1 whenever any site in this sequence changes, but type 1 cannot mutate back to type 0. Okay, and I want to understand the evolutionary dynamics of this system. So I have my quasi-species equation, and since there are only two types, they decouple, and I can just write down the equation for type 0. So if I just use that equation here, so dx0 dt So this drops out of the picture because type 1 cannot mutate back to type 0, And the average fitness has to be written down. Average fitness is okay. So if I plug in the average fitness back into this equation, and I can, just to simplify notations, I write Q. So Q00 is the quantity that I have to determine. So it is a probability that type 0 remain as type 0 during the process of replication. So there are no errors involved. And so if you have a type 0 which is a sequence of length L, and each site can mutate with probability U, so what is the probability that this sequence will remain unchanged? So each site can mutate with probability U. The probability that it does not mutate is 1 minus U, and the probability it doesn't mutate for L sites is 1 minus U to the power L, right? So Q00 is 1 minus U to the power L, right? So this equation, so I want to find out the equilibrium state of this equation. So all I need to do is set dx0 dt equal to 0, and when I do that, I end up with two possible equilibrium states, x0 star equal to 0 and x0 star equal to Now, this is a remarkable result. I'll come to this in a moment, but first reflect on this. What does x0 star equal to 0 mean? I said that x0, the type 0, has a higher fitness than type 1, right? But in the end, you end up losing type 0 altogether. So even the higher fitness variant is lost from the population. And so we want to obtain the condition under which the higher fitness variant is retained in the population, right? And so it is retained when this quantity is non-zero, right? This frequency is non-zero, which means that f0q has to be, it has to be greater than 0. So f0q has to be greater than 1. Right? So f0q has to be greater than 1 is a condition So what does this condition translate to? So I have obtained q as 1 minus u to the power L. So I can write f0 greater than 1 minus u to the power minus L. And if I take log of both sides, so I assume that u is a very small quantity, it's a mutation probability. So I can expand this using a Taylor series and throw out all the higher order terms and retain only the leading order terms. So that gives me UL. So what about log F0? So F0 is the fitness of the fitter variant, and the other variant had a fitness equal to 1. Now, in most realistic biological situations, the fitness of the fitter variant cannot be too much larger than the other one, right? So log of f0 can be approximated to be of the order of 1. So for instance, if f0 equal to 2, this is about 0.7, right? So log f0, if it's approximated to be of the order of 1, so this condition translates to So for the fitter variant to survive in the population, which goes which is a very counterintuitive concept, right? Because there is a situation in this case where the fitter variant can just drop out of the population and be replaced by the less fit variant. The condition that needs to be satisfied is that its mutation rate has to be larger than the inverse of the length of the sequence, right? And this is called Eigen's paradox. So you end up in a situation like this, where if the mutation rate happens to be larger than the inverse length of the sequence, then the fitter variant, so which is there, this is the highest fitness variant, this drops out of the population altogether. Okay, and this is a paradox, as pointed out by Eigen and Schuster, because it led to a conundrum when people were discussing about origin of life. Because in order for a replicating molecule to be viable, it must not be subject to mutational degradation, right? And so it has to somehow figure out a way to avoid the error threshold. So the error threshold has to be small, right? But for error threshold to be small, L has to be small, right? If L is small, the error threshold error threshold is large, right? So for error threshold to be large, L has to be small. But functional molecules have to be, I mean, only large molecules are functional molecules. You don't have small sequences which can encode functional molecules. So that led to a paradox which is as yet unresolved, in the sense that we don't know how large functional molecules manage to evade the error threshold problem. Okay. So this is an example where the common notions of survival of the fittest as expected from Darwinian evolution does not hold. It's an example where which shows that the fitter variant can be lost from the population. Okay.
Did you take that limit ln not?
Oh, okay. So that is because I have taken the fitness of the other variant, type 1, to be 1. So F0 was taken to be larger than 1. Okay. So, but how large can it be, right? So from a realistic perspective, the fitness difference is usually not a fitness advantage of 100% is quite unusual. So a fitness advantage of 100% would mean that F0 is 2, which is of the order of which means log F0 is of the order of 0.7.
So if ln F0 is tending to 1, does that mean F0 is tending to E?
No. So E means I'm just saying that F0 cannot be very different from 1. It cannot be 100 or 1000 or something like that, right? So it's a number which is which is such that log F0 is of the order of 1, and that is a reasonable assumption to make, because the fitness advantage of type 0 relative to type 1 cannot be very large. That's all I'm saying. So this is a back of the envelope calculation. So yeah.
Shubhati, when you say long, cannot be long or cannot be large,
Yeah.
sequence length, what is the order of magnitude you're talking about? Are you talking about hundreds? Are you talking about tens?
So functional sequence depends on functional
Typically, amino
sequences,
acids,
right?
I mean, like proteins are typically 300 amino acids.
Yeah.
So that means you require roughly 1000 base pairs
Yeah.
to code that. So is 1000 too long, too large for you? Or will you say too large?
Yeah. So too large is, I mean, 1000. It depends on what the error threshold is, right? I mean, if it can be if it can, the point is if it also depends on mutation rate, right? So if the mutation rate is not very large, then it can you can have long sequences without any problems, and those long sequences can encode functional properties, right? But the reason it's a paradox is because the expectation was that in the primordial era, uh, the mutational degradation was much more likely. So mutation rates were likely to be high. And so here's a sort of partial answer to the question as to how long is a viable length, right? So this is a list of RNA viruses which are typically not very long, and you can see that the one that I've highlighted is polio, where which lives close to the error threshold. So it has a length of about 1,000 bases, of the order of 1,000, and a mutation rate of about 10 to the power minus 4 per site, per base. So this is a viable RNA virus, well, to the extent that RNA viruses are viable because they have to have a host, and it survives.
No, so the trick it uses to get around this is basically it only codes for very few proteins, and then it uses large number of copies of this protein to create its shell.
Exactly. But that is a characteristic of viruses, right? It cannot sustain itself on its own. It needs the host machinery to survive. But even with that, it lives close to the error threshold. So if you calculate UL, it turns out to be of the order of 0.81. And there was a remarkable paper in 2000 which showed that there's a the drug against a polio virus, which works exactly by pushing the virus over the error threshold. And so this is a drug, this drug was there before, so this study just showed how this drug works. It shows that it works by increasing the mutation rate of the polio virus. So and you can see that it's not very clear from this, but a small increase in mutation rate per genome is enough to push the viability of the polio virus down remarkably. So 50% of the viral population becomes unviable. And so it works just by making use of this error threshold business and pushing it across the error threshold, inducing mutations which push the polio virus over the error threshold and leads to its unviability. Yeah.
So the mutation rate between nucleotides are not same, right? There would be some mutations.
Right.
In some
Right.
So longer sequences are more likely to have, or longer sequences can afford those particular nucleotides in some sense. Is that reason?
I didn't quite get you. Longer sequences can afford what?
Because the mutation rate between nucleotides are not same.
Mm-hmm.
You need to cross certain threshold length.
Right.
Before certain nucleotides can be accommodated. Yeah. Is that because some sequences are rich in, let's say, nucleotide C.
Mm-hmm.
Some are, let's say, more rich in A and G.
Right.
So would that be correlated with the length?
So you are asking if I have a GC-rich sequence, for instance, and the mutation rate from A to T is high, so that doesn't affect the GC because most of the sequence is that what you are asking, made up of G and C?
So if I'm given the mutation rate,
mm-hmm.
and if I'm given the length of the sequence,
right,
does it give some predictability as to with what frequency the nucleotides would appear?
I'm not sure what that means. I mean, mutation, what do you mean at what frequency the nucleotides will appear? I
Because
mean,
if the sequence is short, too small,
so
you can't afford nucleotides which mutate too fast, like this does.
so these are mutations which are appearing sort of during the replication of the genome, right?
Right.
And so during the process of replication, you don't have an exact copy, new mutations are incorporated. And so, of course, there are details like the fact that some nucleotides are have a lower mutation rate than others, and all those, and all that has been glossed over in this description. But the fact remains that this error threshold concept is an important one because it it speaks of the viability of a genome in terms of surviving a mutational degradation.
Right. So if I, in principle, if I wanted to build a longer sequence, for that to be viable, I have to decrease some effective mutation.
You have to decrease the effective mutation.
Which means I have to prefer certain nucleotides over the others. Because some might be more. Is that?
Yeah, I don't think it has been worked out to that extent as to what mutation, what nucleotides you can put in at what site to ensure that the overall mutation rate is lower than the threshold. So this is just a sort of proof of concept calculation, which shows that the error threshold is important when you are talking about primordial times when life hadn't completely emerged as we know it. But then the question arises: how does a sequence which encodes information emerge and remain viable in the face of mutational degradation? Yeah.
You said we can't go from type 1 to type 2.
Right.
Is that a realistic assumption?
No, it is not. This is again a proof of concept calculation in the sense that you can imagine situations where type 0 and type 1 are such that to go back from type 1 to type 0 you have to cross a energy barrier, or the fitness landscape is such that it becomes difficult to go from type 1 to type 0, but not to go from type 0 to type 1.
So, this might be
Yeah.
if prions like this is because type 0 is a more big, if that is the normal configuration, so prions is a misfolded one, but you can't go from prions to
Yeah, but it could be. I haven't thought about it, but this concept was mainly put forward to emphasize that functional molecules. It's difficult to understand how functional molecules came about, because to have functional molecules you need large sequence to encode function. And but large sequences are subject to mutational degradation, and so that's the paradox. How large can be sustained? Like, I think this figure gives some example for RNA viruses, but then it doesn't apply to the primordial times where you have to have viable organisms made of RNA themselves. At that time, there was no host to rely on. Okay, I'm done.